alaikum. Good morning, everyone. It's an enormous pleasure to be here today, especially after Dan's talk, which basically completely set up what I'm about to say, because I'll tell you about actually making real AI with self-driving or autonomous vehicles. I want also to thank you to Alex, to Emily, and to ADIA. I've learned so much in the past 2 days. It's just been a pleasure to be here. So we work in the global supply chain. And since I have a few moments, I'll tell you something interesting. I was a couple of days ago at a conference with leading port operators. We work in the port. And they asked me about our autonomous vehicles and what was going to be the situation in 2040 or 2030. I don't usually think about that. I'm the CEO. I'm thinking about next week. But what was interesting is I realized that this enormous port, the largest single-site container port in the world, is going to be completely dark by 2040. There will be almost no people. There will be an army of people that got dislocated, basically based on the technology that we have. That was kind of a little creepy when I realized it and when I said it, but it's true. In this supply chain, I'm going to show you that we're running a fleet of self-driving vehicles, and it's in the port, and we work in enclosed environments, but it really is going to sweep the world like wildfire because of the value proposition. Now, I have a question. ADIA asked me to talk a little bit about entrepreneurship, which I can easily do because this is my third company. But let me just ask, how many people in the audience are interested in talking about entrepreneurship? Oh my gosh. Okay, well then I will do it. I will leave most of it to the end, but I'll just tell you that I have a lot of education. I came from a modest family, and I've started 3 companies, the first one of which was a failure, and the second one was significant, and the one we're doing now is really major. And it takes a few building blocks to start a company. Let me tell you that I'll be happy to talk to anyone individually after this. I've done it successfully. And it takes grit more than anything else, I think. So I'll give you the building blocks at the end of this. But please think about, when I talk about how we've built the company, what the core issues are. So basically, you need fantastic people. The team is everything. You need technology. I'll talk about tech startups. That's only what I've done. Capital is super important, obviously. So there are key building blocks that you have to check off. So basically, as I said, autonomy is going to come like wildfire. This is a picture of our prime mover. Let's see can you see that? And what you'll see is that it's sensored up. So we have $30,000 worth of sensors on this, and we have turned it into a vehicle that through those sensors sees the world, and through our programming figures out where it's going to go. We keep it safe. Safety is above everything else. It is a horizontal technology platform that is very powerful. Our platform alone, we work in logistics. Ports, airports, factories, warehouses, intermodal rail. So we have implemented in a number of those areas basically with the same core autonomy system. And it's really, as I said, I'll show you the value proposition, but it's going to make a big difference. So this is a picture of some of our fleet. Right now we are running approximately 30 vehicles in the largest single-site container port in the world. This is some of them. You'll notice that they have signs on them. They are also now colored as well, brightly colored. And that is because our partner wants to make sure that it's obvious to people that these are robots. We are running roughly 30 robots amidst 900 human-driven vehicles. And where do you think the problems come from? So the core value prop is here. In our vehicles, our customers tell us that they will save 60 to 70% of the human capital labor in operations. That is an economic dislocation that is a partner to the technological dislocation that this tech will bring. It's just utterly almost unthinkable, but it's true. We're doing it. The other thing is that the robots work 3 to 6 hours a day more than humans do. So we end up with a minimum of 25% more operating time with the robots. And then finally, believe it or not, we can operate this 60-foot-long vehicle articulated with 2 bodies to a 2 to 5 centimeter positional accuracy. My founder and co-founder and partner is in the audience, and he actually wrote the algorithms. But it's mind-boggling. We take a 60-foot-long articulated vehicle and we drive along the center line and we park with a 2 to 5 centimeter accuracy. We needed to do that because in logistics, which is where we play, we have to line up very closely to other equipment, a crane, a conveyor belt, etc. So we had to hit it. The other thing is safety above all. And if you don't have a high positional accuracy for the vehicles, you don't know where they are and you have a safety issue. So this goes fast. It's a video. I'm hopeful that I can press the button and the video is going to go. But this is old video. I wasn't allowed to show the newest one, unfortunately. But this is a camera that's in the cab of that big truck that you saw. So this is a container moving truck. As I said, it's with an articulated ball joint. The 2 vehicles are connected. And you're seeing inside the truck, inside a port. And this vehicle is going to do a round trip. It's going to go navigating itself through this port. It's going to get itself loaded. The container's going to come down on it. It's going to know that everything's safe, drive off, navigate through the port, stop again and park within 2 centimeter accuracy to the crane again for the second time, get offloaded, and then drive itself back to its home. That's what you're going to see, and it goes fast. So here we go. It starts off. It sees the stop line. It stops at it, takes a protected left turn. Now it's driving through the port. Just as you or I would do, it's looking right and left. It's looking for a hole in the traffic. You can see that it's actually a very busy port, and you can see all these other trucks that are human-driven. Now at this point, this is the only robot in the port. It's driving along, takes a left turn. Those gray lanes are the working lanes, which the vehicle has to pull into with accuracy. That big thing, green thing is crane. Watch this. Boom. That's the 2 centimeter correction. You can see that guy's getting loaded up there. Now we're waiting for the crane to arrive. You see it there. Look in the mirror at the top here, up here, and you'll see that the red container gets loaded. There it goes. So that's an automatic loading that's happening because we hit that accuracy of pulling up to the crane. The vehicle has lots of checks that it has to do, and now it knows everything's fine, waited for traffic again. You see the big ship-to-shore cranes. Takes a unprotected right turn because it decided it was safe. It stops because it sees this suspended load. This weighs 8,000 pounds. It sometimes falls off and kills people, so the robot has to know and has to perceive that that's there, and it has to stop. Again, here it is, pulling into the working lane. Again, look for that 2 centimeter correction. There it is. The robot does it by itself. Everything it does by itself, it's waiting for the crane to arrive again. And what you'll see is the inverse. You'll see this container now being taken off the vehicle as it gets unloaded. This port's mission is to move containers. So that's what it does, and that's why this is so important to the port. This is going to replace an army. Now it's just driving back again through the port. This is the yard area, the storage area. We are now also working in the wharf, which is 4 times as complicated. There's the wharf, actually. You can see the big container ship. And so this is the busiest road in the port that the vehicle's about to turn into. There it takes a left turn, and you can see the big ship-to-shore cranes. You saw the container ship earlier, and those are the yard cranes. They're smaller. So it's driving down this busiest road in the port. It sees that car slowed down. You saw that, stops at the stop line. It's going to take a big turn. The port's been set up to make it easy for the trucks to turn. It stops. Why? It saw this. You see, look, it's backing up. The robot was right. It was a threat. So the robot stopped, waited for it, and now it takes the left-hand turn, and it's going to put itself to bed in its home. So this is a real manifestation. We are running roughly 30 of these vehicles 24/7 in the port, full ops, with 900 human vehicles running around them. We just hit human productivity, and we are looking forward to exceeding it. So basically, as I said, we're running in this port. We run about 5,000 containers per week. It's real-world traffic. You saw that there can be very heavy traffic. Sometimes we come within just this much of another vehicle, and we know it, so it's safe. And in addition to everything else, the vehicle system of autonomy is backstopped by an on-demand remote operator system. So if the vehicle has a problem, instead of just stopping, what it does is it automatically calls an operator, somebody picks up, and then they can just usually just give the vehicle a nudge, and it gets back into operations. It turns out that it's much safer for the vehicle to navigate itself using its programming than it is for an operator to have a joystick and control the vehicle. So most people use the joystick because it seems like it's the right thing to do. It isn't. Because our vehicles are so sensitive and well calibrated at this point, 5 years into the project, that they operate way better than a human can operate them. And as you can see here, we basically have tens of vehicles in deployment. Can't give you an exact number. We've moved 100,000 vehicles, and we have driven about 200,000 miles in key autonomy mode. So in terms of performance metrics, we're very metric-driven. You know, we're science guys. And we have tens of vehicles in the fleet, as I said, deployed in real work. We achieved human productivity. My guess is that we will exceed it in 2 months maximum, something like that. We have the positional accuracy we've driven. This is a mock-up, doesn't show, of the remote operator system. They sit there with these huge consoles around them trying to mimic them actually being in the vehicle so they can see what's going on. And we've moved a bunch of containers. So this is the core building blocks of the system. We can actually retrofit or buy new autonomous vehicles. We have sensor configurations and a lot of IP for figuring out how to optimize an autonomous vehicle for the application that we are using. We've actually done work in airports and also in a factory in addition to the port. But we can do basically just about any vehicle. And then you can see there are sensors here. And then this is the core work of my company. We are a software company. But in these early days of autonomy, we had to provide a full scope solution to our customers. But we are a software company. In addition, we have a fleet management. I'll talk about it later. And as I mentioned, the on-demand. So here is I knew you guys are a techie audience, so wanted to show you. This is basically an overview of the platform architecture. You can see at the bottom the software stack. You know, that's the $70 million asset. And so we have 3 layers of it. One is the core autonomy that works for everything. Second is application-specific port, airport, etc. Third is the most small, but it's the customization, because we have to make a map that the robot can follow at every place we go. In the middle, we have a fleet management system, which we've built. And it's one of the first all-autonomous fleet management systems. The key point here that's interesting is that when you take a vehicle that can do things that a human vehicle can't do, like run 24/7, take itself to get gassed up, and so forth, you actually need a new kind of fleet management system. So we're sort of pioneering that, and we expect that we will get enormous efficiency improvements when we can get to one single process. We are basically taking factory automation outside the factory doors. It's another industrial revolution, to my mind. And then we have on the right-hand side a lot of operations tools. We not only have done all the R&D for the autonomy, but we had to go, obviously, into operations. And so I was lucky I was able to hire a guy who had been an F-16 pilot. And he brings that ferocity of excellence to the ops. So we've been pretty lucky with that. And then, in addition, we can basically talk to the site's fleet system or anything else, and that's at the top, the terminal operating system. We obviously have to talk to it and get our job and know where to go. So we do the remote ops, but basically the point is that there are these three levels of the system. This is what we do when we get a new customer. We map. I'll show you an example of the mapping in a moment. We define the system that is needed, specifically the functionalities that that system is going to need. Do I have to load? Do I have to unload? How close do I have to get? What do I have to line up to a conveyor belt? All the details of how somebody wants to operate their environment. And then we test, and test some more, obviously. I used to joke with my team I did not want my face on the cover of Time magazine for a problem. So we test a lot. We implement, and then very importantly, we actually hand off the system to the customer. What we want to do is build it, support it. We have a software business model that is basically a full scope solution. Now, I joke, we are all AI all the time. So basically everything we do in development is AI, and we use these huge amounts of data to do our development and our operations. So 5 million data points per second is what the robot does. And then we use it to build software. So this is a map. Whoops. Yeah, here we go. So this is the kind of a map that we make. We extract the features. We make a feature space map, not a geography space map that like something that we understand. And you can see that we create these very robust features. So we use various standard algorithms and also AI because this is the core of everything we do. The vehicle has to know exactly where it is at any given time. So this is the map that we see, and this is a port. You can see the big cranes and so forth. Now, this one shows you the vehicle driving at the center. So it looks like the world is moving, but it isn't. The vehicle itself is driving. But look at the traffic. This is in the wharf area. Look at all that traffic coming on. And the robot is navigating its way through all of that traffic, turning where it has to, and so forth. You can see some of the other ones turning. The wharf is a particularly chaotic area, mathematically speaking. It has very few rules about where you have to come in, where you leave, where you park, all that sort of thing. So the robot has to be very sophisticated and see all of it and understand how to move in that kind of environment. So these are some of the other aspects of the AI that we have. I like to show you the heavy rain one. At this point, sorry guys. At this point, we've been doing this with our partner for about 4.5, 5 years. So this shows you operations in heavy rain. We actually worked a couple of weeks ago in the heaviest rain that Singapore had had in 40 years. It's basically monsoon level, and none of our vehicles had to stop. So what you can see here is that even the camera is getting blocked by the raindrops, but these trucks are creating splashes, they're creating puddles from the rain. So we have what I think of as tertiary level algorithms, where we actually deal with puddles, because puddles reflect the LiDAR differently. Splashes do things also. So the level of nuance that we are writing into the software is, at this point, why we have an operational system I think no one else really does yet. So this is the real world environment that we operate in. And then this one shows you the other thing that we use AI for. We have censored up the vehicles so that most of the hardware is monitored. Why? Because an 8,000-pound vehicle has to come to a safe stop if there's any issue. And we got a benefit from that, again, based on AI. We can tell when the system components are about to fail, so we can do predictive maintenance, not preventative maintenance, and we actually save a lot of money there. So the AI helps us there. And then finally, that's this one. And then basically the one on the right-hand side, here we go. That green is the right path. So the software of the robot tells it where to go. It finds paths, and it finds the correct path. So all the planning and control is done by the robot. This is obviously the visual from the camera, and you can see this area in here. That's what the robot actually sees. So basically, I mentioned that in addition to the vehicles themselves, we have a fleet management system. We monitor each vehicle, as I mentioned, and in addition, we monitor the fleet. So the point is that we really want to have complete safety, and we want to also optimize productivity. So we have a lot of proprietary technology. The technology development is all driven by AI, as I mentioned. We can actually work in mixed human-robot traffic. It's harder. A lot of companies at our stage can't do that yet. Very importantly, we have built this whole system without putting in any additional hardware or infrastructure in the port. So we use the features that are there, not other pieces like buried pieces or structures that give signals or anything like that. We don't do any of that. So everything we've done, we basically built through algorithms, because that's what our partner wanted, and we were able to do it. But it saves probably $10 million in installation. I mean, so that was a big savings for our customers. In addition, we can retrofit a vehicle or buy new. We, at this point, have a lot of expertise about what makes a good autonomous vehicle on the hardware side. We can operate in heavy rain and weather, as I mentioned. We have a universal software stack. Very importantly, we can operate in an environment that's changing. That's important because in the real world, everything changes. If you have another new road, we have to figure that out, but we can operate and we don't have to stop. Finally, the port's enormous. This is 4 or 5 kilometers on a side, and you saw the size of a slot. So we actually have to navigate through 9,000 different operating slots. To the vehicle, each one of them is new and different, so the vehicle has to know how to pull into and pull out of 9,000 different slots. So we actually built scale mapping tools to be able to deal with that issue. Then safety, of course, is always a top priority, and so we've done a bunch of studies to show that. This one, I can't get it to run. Oh, there we go. Watch this. You see the dummy on the right-hand side next to the vehicle over here? This is very hard to see because it's just standing right up against the vehicle, but you can see that the robot recognizes that there's a person there and that went around it. That's actually pretty hard for the robot to do. Let's try this one. Nope. Is this it? Yes. Okay, so see the robot is coming. It wants to take a right-hand turn, so it's getting ready. And look, a pedestrian, looks like Elvis. Pedestrian comes and the robot stops. And then the pedestrian keeps coming. The robot continues to be stopped. You notice that the sign says stopped. And then when this pedestrian is out of the way, the robot continues its journey. So, you know, safety first, repeated. Safety underlies every algorithm, every piece of the system. So we found it out of MIT, just to talk about the company for a moment. That's Daniela Roos. I think she's known to a bunch of people here. And this is her in her lab. She's a leading roboticist. And so in 2010, she and Google invented autonomy for the first time. And we started this company about 2019, and we've been working with a big port operator. I wanted to say just one other thing that's based on the interesting discussion yesterday Alex talked about the global supply chain. These vehicles save 60 to 70% of their human operating cost. But more than that, they have a level of, I don't want to use perfection, but a level of operating accuracy that takes out so much of the chaos from any of these supply chain processes. And they work virtually 24/7. So when the question was asked yesterday, what do we do for sustainability? How can AI help sustainability? Autonomy is one of the first real applications of AI. We use AI and classic algorithms to get the benefit of the AI as well as the rigor of the algorithms so we don't make mistakes. But imagine that dark port that I talked about. That's going to be a reality with these vehicles because they can offload the ships with the cranes. The trucks can be right there lining up. The system tells the truck where to go. It can get offloaded, as you saw, with a crane without a person. And then the truck goes and does its next thing. So this is really going to come, not immediately, and it'll depend on geography, and the value prop depends on people, so it's really for the industrialized world. But it is another technological revolution. So thank you for your interest.
Thank you, Dr. Wyle. Any questions?
He's serious.
Thank you for the excellent presentation. I have a question. How does it work from the legal point of view? Because I'm convinced that technology is excellent and let's say the improvement in safety is massive. But let's say hypothetically that one of your vehicle damages some property of the port, or even worse, injures a human port operator. So what happens at that point? And is it country specific? Because it has to do with the laws of the country at that point.
I can't answer exactly the question, but I'll give you the data that is adjacent. We work in enclosed environments, ports, airports, factories, warehouses, intermodal rail. And so they are private environments with private roads. That was a choice I made for reasons that you allude to. So far, we've been pretty lucky. Legally speaking, It's a complex situation when someone gets hurt or killed, as we saw in the United States. And we, so far, have not run across that situation. I think in terms of liability, the answer is it would depend, because we've got a system that's built by software and we would have liability. The other interesting thing is that the insurance, to my shock, is really inexpensive. And that's because insurance companies work on past data. So that's their decision. I appreciate it, but that's the only thing that I know about that. So I can't answer the specifics of your question other than to say it varies by country. It varies in the United States. It will vary by state, probably local jurisdiction, but we're in enclosed environments and we have a lot of insurance.
Congratulations, Heidi. It was an excellent presentation, an example of vertical applications of AI with in a regulated environment, which make it easier to adopt. My question is, there are several strategies in the market to achieve autonomy on vehicles, particularly in trucks, especially the differences are on the guidance technology. There is optical, magnetical, laser-based, and I understand in your case is a mixture between sensors and AI training and computer vision. And that probably it's a high accuracy, but probably the downside can be
Higher what?
high accuracy and accuracy.
Oh, accuracy.
High accuracy. And probably the downside can be excessive computing capabilities consumption and the need for internet network to be always on. So how are you solving that? I mean, what are the requirements for connectivity that your system requires? Are you processing all this information in the cloud or in the edge? And that requires a different network deployment.
Right, so we have dealt with that to some degree based on a different priority, based on a priority of safety. And so our core autonomy system runs in a computer in the vehicle. And we did that because I didn't want to be hacked. So we do send data back and forth, but it does not include any of the core autonomy or the ability to drive the vehicle. So that's a big piece of it. In terms of the connectivity, we do have connectivity at a lower level with the fleet management system, the terminal operating system, all of that. And that we have learned to operate in the environment, even in places where there's no signal for some short period of time that's manageable, because the signal is quite variable. So we've built a system on the software side to deal with the fact that we know we're going to get lousy signal in some places, but so far we've never been stopped by that situation. So I think as we look forward, our partner basically tells us that the issue of power is going to be something they have to deal with, of energy, but we can't do anything about it. It's their facility. So, we've chosen our little playpen so that we can develop the system right now, and we don't have those big issues because the operator handles them for us right now by choice. These are diesel vehicles. We are getting our first 6 electric ones in a few months, and we will use those. It's much better to do electric. And as I said, for me, listening to yesterday's discussion about sustainability, I'm thinking, wow, here we are. This is going to make a big difference. We are in enclosed environments. I frankly am not interested in being on the roads, to be honest with you. I mean, let the robotaxi people do that. We have 10 years, 20 years ahead of us in terms of these enclosed environments. So, that's what I chose because I want it simple.
Can you build a self-driving ship?
We can't. Different technology. Ship? Like big ocean ship? We can't. Because everything we do is based on features of the road. I don't know if you noticed, but we actually drive literally right up the center of the road. The vehicle's very, very accurate. Thank you. Oh.
Well, as you said, the automation is going to sweep through the world like a wildfire. And maybe, arguably, it's not your job to think about that, but, what can we do with all the people who will, lose that kind of jobs? Not everybody can be a techie, right?
It isn't my job, but I care. And so I'll give you the short answer, which is somewhat of a cop-out, but in reality, it's a true one. What turns out, remember that remote operator console? We use drivers to man the remote operations consoles. And in reality, it turns out that people don't order 1,000 vehicles. So I'm talking to a very large US railroad. They're going to order 700 to 1,000 vehicles when they build their facility. But right now, they start with 2, and then they go to, tens. And all of the drivers that we've displaced so far have gotten jobs as remote operators or annotators or so forth. So there will be tech-level jobs, not software engineer jobs. But when this technology gets large, it's an army of people. That's what happens in technology revolutions. But we don't have that problem yet.
Just for your peace of mind, currently in Europe, we have a shortage of 230,000 truck drivers. That it's projected to be almost above 700 when people retire. 100,000 in 2030, because this is not a desired profession. Yeah. People, have to sleep in their trucks, in roads that don't have showers. So as long as those truck drivers retire, the young people don't want to become truck drivers. So this will be also very beneficial for replacing the shortage.
It's 80,000 in the US right now, shortage of drivers. Somebody said something.
We'll take one more question over there.
Thank you for the presentation. Just a question out of curiosity. So does the software or the AI track the maintenance requirements for the trucks, or is it something of the responsibility of the port operator? Thank you.
My CSO, smartest guy.
Hello. Yeah, maybe I can answer this question. Yes, because to a degree, as of now, like especially as compared to manual drivers, to manual trucks, like we need to monitor a lot of things that is not needs to be monitored. If a safety driver is sitting inside a cabin, for example, the temperature of the cabin, like whether the door is open, whether the glass is open. So we are monitoring all sorts of signals from the vehicle, and based on the at the same time, like we are logging and keep on tracking of all sorts of signals from the vehicle, and based on the trend, like we are actually like able to predict like when certain things or when certain sensors is going to have problems or issues in advance time, so that like we can do this kind of predictive maintenance activities instead of now majority of the maintenance is based on the like a certain mileage of driven or a certain period of driven, which sometimes your components is still in a good shape, but because the time is up, so you have to change it. But with the new technology that is coming, we analysis and we do assessment like based on the trend, so that like we don't need to change the components if it's not necessary. Yeah. Okay. Thank you.